Hi guys, and welcome to today's video on differentiating negative powers. Yes, we are here differentiating negative powers. And you're going to say, wow, that's a little bit excited. Well, differentiation is my subject. I love it, love it, love it, love it. It's been dealing with differentiation from first principles, the shortcut for differentiation, finding gradients of tangents and points, blah, 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 which has all been talked about in that video over there. But do me a favor, don't click that link. A card will come up above me that you can click if you want to see that video, or there's undoubtedly a description below that I will add for you to go straight to it. But this is a continuation of that video. What do I want you to be able to do by the end of this? Well, as normal, it's directly above me, and I want you to be able to know what it means for a function to have a negative power. Many times in maths, if you can understand why you're doing this stuff, it makes things a lot easier for you. How to turn a negative power into a positive power, and vice versa. How to differentiate a negative power, and why we need to write certain notations in certain ways. Now, a recap of a lesson stated that differentiation is about finding, as I say here, the gradient of a tangent to a point. All right, so the gradient of a tangent to a point. And having done sort of differentiation by first principles and finding that really long, and good news is it's highly unlikely there'll be lots and lots of those questions in any exams. They might put one in, but it's just a process. There's better ways of doing it. We then came up with a shortcut that said, well, look, if I had a function in some form of x to the power of n, the shortcut that can be expressed as f dashed of x, y dashed, or dy by dx is given by n times x to the power of n minus 1. So, for example, if I had f of x was equal to x to the power of 6, then I know that f dashed of x is equal to multiply the power by the coefficient, which is 6, not 0, x, and take 1 from the power. So that's 6x to the power of 5. What that tells me is to find the gradient of the tangent of any point on that graph. All I need to know is an x coordinate, and I can find that gradient at that point. So, and in words, we've gone to say the multiply the power by the coefficient to create a new coefficient and subtract 1 from the power. That's really important. Negative powers actually come up in differentiation all the time, but the point of it is you sort of need to understand what a negative power graph is. One of the graphs I want you to consider for the moment is 1 over x. If I draw the graph of 1 over x, as I've got it here, you'll notice that the graph goes up and further down, and it goes down to infinity on the y-axis and negative infinity, but it seems to never get closer and closer to that line. Why? Well, it has everything to do with the x being on the bottom of that graph. What one value do we never like to be on the bottom of a fraction? And that is 0. Why? Because when you divide by 0, what do you get? Well, either infinity or, more importantly, or probably more correctly, an undefined value. So we don't like the x value to be 0. So that would suggest, bearing in mind we are differentiating to find the gradient of the tangent to a point. If there is a point that doesn't exist, then we can't differentiate at that point. We can differentiate at all other points, but we can't differentiate at that point. And actually, that's sort of where we're going with this lesson. The idea that 1 over x actually can be turned into a negative power. But while we can differentiate it, we need to be aware that there are certain points in that graph that cannot be differentiated. Okay, so when I was at school, I had a fabulous teacher by the name of Mrs. Hurst, and she was the only teacher who ever made any sense to me, all right? I also had a small bit of a crush on her, which is way too much information for this video, but she basically turned around and said, we can turn any negative power into a fraction by doing the following thing. Turn the negative into a 1 over. And I was like, that's freaking awesome. So, for example, x to the power of minus 1, she said, take the minus sign, put it as a 1 over, and then copy everything else down. So x to the minus 1 just becomes 1 over x. And she was like, oh, x to the minus 2 becomes 1 over x squared. And x to the minus 3 becomes 1 over x cubed. And I was like, I can do this all day. This stuff's freaking awesome. X to the minus 10, 1 over x to the power of 10. The only problem was, with shortcuts, they tend to fall apart at some point unless you understand what it is you're really doing. So I sadly got to the point of 2x to the minus 2, and me being me, at that time I write, oh, well, that must be 1 over 2x squared. What I thought she meant was take all of that term and move it underneath the brackets and just put a 1 on and a line on top, but sadly that's wrong. Right? What she meant was, it is whatever the index, the power, the negative number is connected to, that's what moves below. So 2x to the minus 2 That minus belongs to this term here, so the 2 stays where it is, and then I divide that by x squared. Now, once I understood that, I was like, oh, that's flipping awesome. So 4x to the minus 6 became 4 over x to the 6, and 8x to the minus 10 became 8 over x to the 10. Now, that was awesome. And she said, well, what we've really done is we've moved a number from the top of a fraction to the bottom. Right? That's all that minus sign has done. It's taken from a negative 2 on top to a positive 2 on the bottom. And she was like, well, what we can do one way, we can obviously do another way. And I was like, oh, awesome. So if I had 1 over x squared, then I know, well, it's x squared underneath, so that becomes 1 times x to the minus 2 on the top. If I had 3 over x to the power of 4, the 3 was already there, and I times that by x to the power of minus 4. I have the positive 4 on the bottom, negative 4 on the top. And lo and behold, that's actually the basis for all the work we're going to do now. And as I say here, that suggests then that a function of x, which can be written as 1 over x, can now also be written as x to the power of minus 1. And I'm like, yay! Because as soon as it's in this form, I can go back to the fact that if I know that f to the x is in the power of x to the power of m, that f dashed of x is given by nx, n to the power of minus 1. Oh! So I now know I can differentiate that by following my rules. This times my coefficient gives me minus 1, times x, and take 1 off the power is minus 2. OMG, this stuff is amazing. And that's actually as simple as it gets. Now, please be very careful. When you have negative numbers, remember that when you take a 1, don't make it 0 in that situation. Lots of people make silly mistakes by adding powers. I don't fully understand why. Now, to make this go back to a positive power, and sometimes exams ask you to express your answers in terms of a positive power, that minus 1 stays, and I can move the x to the minus 2 underneath to become 1 over x squared. Now, just because I can, I've gone on and actually shown you what the differential function looks like. Now remember, when we have 1 over x, we said there would be a point that couldn't be differentiated. And if you notice here on my function, we notice that there is an asymptote for my differential function. So my function of x was 1 over x. My f dashed of x was minus 1 over x squared. And again, if I put an x value in here and square it, then what do I find? Yes, 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 I find that that point doesn't exist. And the good news is that you can prove that that graph does not have a point there. So while you won't be expected to draw these, I would ask that you just remember that when you are differentiating and integrating, you're dealing with actual functions, and just try and work out what it is they look like. Now we can check this type of stuff with a CAS, which is awesome. And we've used the idea of the CAS before. So going back to my example I just said, f of x is equal to 1 over x. Using my CAS calculator, I get this define idea. I can define a function as 1 over x. That done basically says, the calculator is basically saying, yeah, I've done that for you now. Now what do you want me to do about it? Using my keyboard, and this was all shown in a previous video, I can now say, well, can you do me a favor, calculator? Can you differentiate my function? And lo and behold, out comes 1 over x squared, or minus 1 over x squared, which is exactly what we're expecting. And what does this little doohickey mean? Doohickey, that's an awesome word. Well, what I'm now saying is differentiate the function. So d by dx, differentiate my function. And then tell me what happens when you put x equals 0 into that answer. And undefined comes out because if I have minus 1 over x squared, and I put x as 0 in, then I'm obviously going to get a value that becomes undefined. The CAS calculator is awesome, and again, I can't say enough. Work out how to use that define, whether you're on the TI Inspire or the Casio ClassPad or whatever calculator you guys use. If it has these type of functionality, then use it. So, drawing to the end of this video, a couple of examples just to show the power of this stuff. Here is my function. Now, first things first, I notice I have a fraction. I have an x on the bottom. So the first thing I'm going to do is I'm going to say, right, let's turn all of those so that I have negative indices. X cubed stays as it was. 1 over x squared becomes 1 times x to the power of minus 2, minus 3x I don't need to do anything with, and plus 7. Having got that information, can I now differentiate it? I should go. So f dash of x becomes 3x squared minus 2x to the minus 3. Remember, I'm doing the minus 2 times the plus 1, and then taking 1 off the power. Minus 3, and the plus 7, because it's a constant, say bye-bye. Then I turn my function into positive powers again. Now again, it may not always ask for that, but because they gave it in terms of positive powers, I'm going to turn my answer back. And there we go, there's my differentiated function. So I can now find the gradient of the tangent at any point there just by having a value of x. So if I wanted to find the value of the gradient when it's equal to 1, I'd have 3 times 1 squared minus 2 over 1 cubed. Let's try that again, 1 cubed minus 3, which gives me 3, minus 2 minus 3, which gives me minus 2. Now again, what do you think will happen if I do f dashed of 0? Well, it's going to be undefined. Why? Well, because we've already found out that in this situation here, that graph is not going to be defined when I have an x value of 0. It just doesn't get defined there. So if it's not defined at the point x equals 0, it won't have a gradient at the point x equals 0. Last question before we finish for this particular video. So 3x to the minus 3 plus 2x squared minus x plus a half. Now I deliberately put that fraction in there because how many of you would have wanted to go 1 times 2 to the power of minus 1? You could have done, but actually because this is a constant, I know it's going to differentiate to nothing. It's going to disappear. So I now can say that f dashed of x is equal to minus 9 x to the minus 4 plus 4x minus 1. So again, minus 3 times 3 gives me the minus 9, take 1 off the power. 2 times 2 gives me the 4, take 1 off the power, and that differentiates to 0. And finishing it off, f dashed of x gives me minus 9 over x to the power of 4 plus 4x minus 1. All right, ladies and gentlemen, that is it. This video is now done. What have we dealt with today? We have looked at differentiating negative powers, but with the context of looking at it in terms of graphs. I can't say enough. Please, please, please make sure that whenever you do methods, be it methods 1 and 2, 3 and 4, or any particular core or pure subject, everything you're dealing with is actually a graph. And if you can just get that, life will be so much easier. Well, that's it for this video. It's been really good seeing you. Thank you very much for taking the time to watch. Have you already subscribed? No? Well, there we go. There's a little button there for you to subscribe. And if you haven't, and don't worry about it, it's all good. There's a video loading up over there for you. It would be good to see you again, however. So, take care, and I'll see you in the next video.